Copy you. Go for APU pre-start.
Roger, and APU
The Space
up
Shuttle
and running, look good on board.
are key to the routine and economical use of space for scientific, defense, and commercial purposes. The orbiter is a space-going cargo vehicle, which will return to Earth and land like an unpowered airplane. It will carry a crew of from 2 to 7 men and women. It can achieve orbital attitudes of up to 350 miles. In its 60-foot by 15-foot payload bay, it will eventually carry cargo up to 65,000 pounds into low Earth orbit. To lift this massive vehicle into orbit, to allow it to maneuver while in orbit, and to bring it back to Earth, it takes power. The raw thrust of rocket propulsion. There are 4 separate propulsion systems on the shuttle. Twin solid rocket boosters support the orbiter and external tank on the launch pad and provide most of the thrust for the first 2 minutes of liftoff and flight. The main propulsion system, a cluster of 3 liquid propellant rocket engines mounted aft on the orbiter. The main propulsion system is supplied liquid hydrogen and liquid oxygen from the external tank. The orbital maneuvering system, mounted in 2 pods on the aft fuselage, produces propulsion for the final stage of ascent, major orbital maneuvers, and retrofiring for descent. The reaction control system, consisting of 44 small rocket engines mounted in clusters in the nose section and in the 2 rear pods, provide thrust for aligning the shuttle while on orbit. The solid rocket boosters are the largest of their kind ever built, nearly 150 feet long and over 12 feet in diameter. They are also the first built for use on a United States manned spacecraft and the first designed for reuse. The solid propellant is contained within the booster casing. It looks and feels like the hard rubber of a typewriter eraser. The boosters are assembled from 4 seamless segments of half-inch steel, lined with heavy insulation. After ignition, the motor is up to full operating pressure in less than 1 second. Each booster generates a thrust of nearly 3 million pounds at liftoff. The main propulsion system represents a major technological advancement in engine design. In the past, rocket engines were usually used only once. These are the first engines designed for reuse, to be flown on 55 missions before needing a major overhaul. For their size and weight, the 3 main engines are the most powerful ever built, each producing 375,000 pounds of thrust at liftoff. A space shuttle main engine has an internal chamber pressure of 3,000 pounds per square inch, 4 times that of previous rocket engines. The thrust can be varied from 65 to 109% of rated power to tailor engine performance for different payload weights, to keep acceleration rates within comfortable bounds, and to give additional thrust for contingency situations. The 3 main engines can swivel 21 degrees up and down in the vertical position and 17 degrees from side to side to steer the vehicle during flight. The liquid hydrogen and liquid oxygen these engines use for propellant is contained in the external tank. This structure is just over 154 feet long, with a diameter of nearly 28 feet. It is constructed of aluminum alloy, up to 2 inches thick. It is actually 2 propellant tanks connected by a cylindrical collar called an inner tank. The forward tank holds 140,000 gallons of liquid oxygen at minus 297 degrees Fahrenheit. The aft tank holds 380,000 gallons of liquid hydrogen at minus 423 degrees Fahrenheit. These tanks feed propellants to the main engines through fuel lines almost 1.5 feet in diameter. The tank is covered with insulation to help keep heat from reaching the propellants and causing excessive boiling, and to prevent ice from forming on the outer surface during launch preparations.
17, guidance release, 15, 14, 13, 12, 11, 10, 9. We have ignition sequence start.
When the main engines have reached 90% of full thrust, the solid rocket boosters will ignite and the shuttle will lift off. A combined thrust from all engines of over 7 million pounds, pushing it toward orbit.
Firm roll, bud. Roger, on a roll.
Just under a minute into the flight, the thrust of the solid rocket boosters will be reduced by approximately 1/3, achieved by a change in the shape of the solid propellant. This, plus throttling down the main engines, will keep stress and atmospheric heating on the shuttle within safe limits. 2 minutes into the flight, the boosters will burn out and be jettisoned.
Okay, SRB step at 212. Step flight. Roger, on step.
They will parachute to a water landing.
Output bias on RGA4 and the roll axis, no problem at this time. We're also seeing an error in IMU2C.
To be recovered and prepared for their next flight.
Columbia, we have a data
After the solid rocket boosters separate, the orbiter and external tank, with engines still firing, continue to near orbital velocity at about 70 miles above Earth. The main engines will burn for 6 more minutes, then cut off. Almost 1.5 million pounds of liquid hydrogen and liquid oxygen have been consumed during the first 8 minutes of flight. Now the external tank will be jettisoned and fall into a predetermined ocean area, the only major component of the shuttle vehicle not recovered for reuse.
Okay, Houston, we're nominal target.
After the main engine shut down, the 2 engines of the orbital maneuvering system ignite. Each delivers 6,000 pounds of thrust for the final portion of ascent into Earth orbit. During the mission, these engines will be used for such major maneuvers as circularizing the orbit, rendezvous with other orbiting spacecraft, changing orbits, and finally for the burn out of orbit and return to Earth. The fuel the orbital maneuvering system engines burn is contained in tanks within the aft pods. This fuel is hypergolic. When mixed together, it ignites. The combined thrust of the orbital maneuvering system engines is 12,000 pounds. Once in orbit, the reaction control system will control the attitude of the orbiter and be used to make very small maneuvers. There are 38 main thrusters with an output of 870 pounds each, and 6 vernier thrusters delivering 24 pounds each. In the nose section is a cluster of 14 main and 2 vernier thrusters. In each rear pod, a cluster of 12 main and 2 vernier thrusters is located. The reaction control system uses the same type of propellant as the orbital maneuvering system. A crossover network enables propellant to be transferred from one system to the other. The reaction control system will be used to bring the orbiter to the correct attitude for entry. The orbital maneuvering system will be used to reduce the orbiter's speed and bring it down into the Earth's atmosphere. During the entry phase, atmospheric friction on the orbiter, slowing from an orbital speed of about 18,000 miles per hour, will generate surface temperatures of up to 2,600 degrees. To maintain the correct attitude during this critical portion of the flight, the reaction control system will be used. Once through the heat of entry, the orbiter becomes a glider, using aircraft-type controls. the jobs of the propulsion systems are finished.
Okay, 200 feet, Joe. 20 feet.
Until the next flight.
10 knots, 200 knots.
4 feet.
190 knots. Speed brakes are tracking.
Down.
That was a super one.